Добрый день. Мы продолжаем наши визионерские лекции о передовых направлениях развития цифровых компетенций в промышленности. Сегодня у нас прекрасная лекция, которая будет касаться непосредственно вопросов, связанных с металлургическими процессами. И слово я предоставляю сегодняшним ведущим с трансляции нашей сегодняшней лекции. Это Вячеслав Котов. Вячеслав, принимайте стартовую палочку ведения сегодняшней лекции. Ребята, как обычно, мы работаем по правилам, что если у вас возникают вопросы, вы пишете их непосредственно в YouTube-канале, мы их транслируем, и наш сегодняшний спикер будет отвечать. Периодически будем делать так называемые, как мы говорим, паузы в словах. Я желаю нам удачи и прекрасной лекции. Вячеслав, вам слово. Представьте, пожалуйста, сегодняшнего нашего спикера. Я думаю, вы это сделаете гораздо лучше, чем я.
Так, добрый день, коллеги. Добрый день, коллеги. Да, с удовольствием представлю нашего спикера. Сегодня выступать будет представитель компании Mecas ESI, Чешская республика, Vlastimill Kolda. Это руководитель направления по литейным технологиям. То есть это человек, который занимается математическим моделированием в области литья и, собственно, наш основной спикер в области цифровых технологий именно в литейном производстве. Значит, наша цель, собственно, нашего мероприятия – это показать, каким образом цифровая трансформация развивается в области обычных, скажем так, более приземленных процессов, то есть когда мы говорим именно о технологии изготовления изделий из металла. И вот мы посмотрим, насколько именно цифровая трансформация перешла в эту область. И, собственно, второй частью это продемонстрировать компетенции в области математического моделирования процессов литья и каким образом это помогает современным литейщикам, собственно, разрабатывать новые технологии, новые оснастки. Значит, как Валентина и сказала, вопросы, пожалуйста, задавайте в чат. Я буду смотреть и, соответственно, адресовать их Vlastimill'у. Доклад сегодня будет выполнен на английском языке полностью, и единственное, чем я могу помочь, это в моменты, скажем так, пауз, я немного буду суммировать то, что Vlastimill сказал, и, собственно, транслировать это на русский язык. Вопросы, опять же, мы можем задавать как в ходе самого мероприятия, так уже и по завершению, после того, как Vlastimill покажет свою презентацию. Пожалуйста, слово Vlastimill'у, и будем начинать.
Hello, good afternoon, everybody. First of all, I would like to thank you for the opportunity to have such a lecture on Ural Federal University. Thank you for this. My lecture will be somehow focused on the digitalization of the metallurgical processes. I will show some examples of digital twin, and I will speak about digital twin at all, like the generic concept of this, and I will show some examples of the digitalization of the casting processes, because I'm like in the first place I'm kind of expert in this field, working almost 15 years in a company which provides simulations for this field. So let me somehow summarize what the lecture will be about. First of all, I will introduce the concept of Industry 4.0 and the digital twin itself, like the generic point of view. Then I will somehow try to switch to the focused especially for the casting technology, for the casting production. I will show you what are the tools which engineer can use in these days for the design, for the creation of the new parts, for the, let's say, validation of these parts from the castability point of view using co-design approach. And then I will show also the tools which can be used in the early stage of the process development and I will focus on a high pressure die casting technology. I will make a small introduction of this. I choose this one because it's like most progressive technology of the casting, where the focus is to have the parts lightweight and structural parts for the cars. So it's somehow connected with the automotive industry, and from this point of view, it's like can be interesting. And I will finish my presentation with the summary of what tool can be used by engineers from the data collection and validation and analysis. I mean the production data which are coming from the machine during the products during the process of the Hyperscale casting technology. So first of all, just to give some clue where we are right now, I have this slide which shows the development of industry from 7th century, where somebody can call this age industry 1.0. Wait, you just have some inputs, some machine which process the inputs, and you get some product at the end easily. In the industry 2.0, the horse was somehow substituted with the car. The amount of input was of course much higher. There was the industrialization from the plant point of view. So there was like production lines, the power plants somehow feeds the plants supporting the production, and the production of the parts was much bigger in amounts and whatever. This is industry 2.0, and then what is already like what is more close to our age is industry 3.0, where all these processes were somehow supported by the robots, automatization, CAD modeling, so computer aided design. Simply the production could use much more tools which came from the automatization and computer aid for the process. And what is what is right now, what is happening is we call it industry 4.0. It's I'm using the term tomorrow, but it's already a few years. It's a known era where we collect the data from all these parts of the production process. We can somehow collect, and based on this data, we can use this data to optimize the production itself. So this is something which is very common for this idea of Industry 4.0, to have, let's say, some cloud which works as a the one source of truth for a whole process, and can be used for optimizing the process, for improving the process, and that's it basically. Worldwide, this trend, Industry 4.0, this is a global idea. It's maybe called Industry 4.0, but this is just the name which was somehow think of in Germany. But any other country worldwide presented already some strategy for industrialization and for the digitization of the industry. Very same approach as was somehow explained on the previous slide. So we really have the worldwide movement, and the industrialization is happening right now, and the digitalization. The ideas of Industry 4.0 was somehow represented by 9 different pillars. I can name it. It's autonomous robots. It's one of them. Simulation, so the support of the production by the simulation. It's the second one. System integration. This is a system modeling where you can somehow analyze or describe the different systems, hydraulic, thermal, whatever. Internet of Things. This is probably something where like the most people somehow connects the Industry 4.0 with the Internet of Things, that you have some communication between different machines, between different things, computers, people, of course. So this is it. This will go hand by hand with the cybersecurity, cloud. There are new manufacturing approaches like additive manufacturing, and the, let's say, 8th pillar can be virtual and augmented reality. So it means that the visualization and the way how we can use the data, visualize then and use it was again quite increased. And of course, when I spoke about the cloud or some single source of truth for all the data collection, we need some tools to analyze such a big amount of data. So this is a 9th pillar of this idea, big data analytics. And there are companies in the world which somehow offers the solution for each from these 9 pillars. There are also some companies, ESI, my company is actually one of the pioneer of this approach to somehow present the solution for each 9 pillars, combining it and somehow introduce the most advanced approaches in presenting of this Industry 4.0 ideas. I will show some examples later. This brings me to the concept of digital twin. Digital twin is something was created, or the idea was formed on the University of Michigan by Dr. Greaves in 2002. It was named at the time digital twin, but actually what it means is that the real space can be somehow not substitute, but like fill in with some virtual space approach. If you, for example, think about the car, these days car collecting the data, sending the data to the service, and this can be with everything, imagine with many things in our life. Simply you have some real thing and the virtual model which simulates the real thing, but not only, it also use the real data to simulate it and optimize it and find some better solution which can be then used in the real space again. So it's a combination of the real and the virtual space. And if I can show one example, this is the picture from the video which can be found on the YouTube, done by GE. This is a steam turbine. I don't know how many similar turbines are installed across all the United States. Maybe it's like definitely more than 100. And this is a nice example of digital twin, because this 100 plus real steam turbines installed all over the country. It has some digital twin. It has some mathematical model which somehow collects the data from all these 100 plus steam turbines and use this data to learn something what can happen in reality, but in the virtual space. And if it learns such a thing, it can then be used for, let's say, for the reasoning, for optimizing of the process. We can divide this work to 3 different areas. The C area would be to collect the data and somehow use it for the learning of what happened, what can happen. The second thing is the model can use this data to predict some states, to optimize the operation run by playing with the steam temperature, rotation of the rotor of the turbine, whatever. And then, of course, it can apply these approaches after some interaction with the people, with the, let's say, somebody who operates it, and really provides some improving or action to be used in reality. But this is a case of, let's say, turbine steam. This is one product which maybe somebody can easily think about how this virtualization or digital twin can happen. But if we speak about manufacturing process, casting, for example, it's not maybe so easy to let's say imagine how this digital twin should work for something like this. So let me maybe right now we will make the pause, and Mr. Kotov will try to summarize this in Russian, and then I will continue.
Да, спасибо большое. Значит, в первой части мы, собственно, посвятили время, значит, этапам создания, скажем так, индустрии 4.0 и цифрового двойника. Если мы говорим об индустрии 4.0, то мы прошли несколько этапов, соответственно, с 1 по 4, и если вы обратили внимание, каждый этап происходит все быстрее и быстрее, то есть время между вот этими индустриями, она стремительно сокращается. И 4-я индустрия, как ее назвали именно в Германии, это индустрия, которая связана прежде всего с искусственным интеллектом, с машинным обучением, с системой виртуальной дополненной реальности, с математическим моделированием, с анализом больших данных и промышленным интернетом. То есть все эти вещи, которые сейчас входят в наш лексикон, они как раз являются частью индустрии 4.0. И одним из основных ключевых элементов индустрии 4.0 это концепция цифрового двойника. Значит, по самим цифровым двойникам идея создания цифрового двойника, ну, собственно, лежала на поверхности, когда начало развиваться математическое моделирование, и состояла в том, чтобы создать как можно более точную цифровую копию реального изделия, основываясь на данных, которые с этого изделия поступают. Поэтому, если мы говорим о цифровом двойнике, то мы говорим о технически сложном изделии, насыщенном датчиками и сенсорами, которые считывают его состояние и могут его передавать. Соответственно, именно для таких объектов, будь это двигатель, будь это автомобиль, будь это самолет, будь это, например, корабль, то есть вся та информация, которая у нас может накапливаться в объекте, позволяет создать его цифровую копию. Ну и вот пример, который был приведен, это генератор, турбина, и здесь цифровой двойник создан для большого количества генераторов на территории США, и основная роль его в том, чтобы получать информацию, собственно, самого генератора, превращать ее в причинно-следственные связи, затем, собственно, на базе этой информации мы можем создать объект, который будет реагировать точно так же, как и реальная турбина, и затем, используя уже этот объект, мы можем информировать оператора, предупреждать, ну и создавать автоматические цепи контроля. Спасибо. Vlastimill? Vlastimill, yes, please switch on microphone.
Yes, for sure.
Okay.
It doesn't work for me at all. Okay, so if we, so this was a case of steam turbine. And as I said before, it's not so easy to imagine the similar thing connected with the manufacturing production, with some product like the casting casting process to be described as a digital twin. But as you can see on this slide, we have some typical case of Hypershy die casting machine. I will describe a little bit later on the next slide what is the technology about. But this machine is simply created from many systems. There are like hydraulic system, pneumatic, like much more. Like you can simply imagine as any different machine which is used for the production of anything. And of course, this machine is just the way how you will create the casting. It's usually used for aluminum casting, aluminum material. And the thing is how to describe this machine in the virtual space. So first of all, we have some system modeling. This can be one of the parts where we introduce all this system, as I described before, in a way of just system modeling, which means that you are able to optimize inputs, outputs of each system, make the different analysis of what happened if one system is somehow broken or doesn't work properly. And this is one way. Yeah. Second, which can be also imagined, is the simulation of the casting process, because of course you have some, let's say, permanent mold, which is put in the machine and then is used for creating a different casting. And if you simulate the process with every possible aspect which happened during the production phase, you can say, if at the end of the process is the healthy casting and the casting which can be used in the application, in assembly, whatever, that you can find by simulation some reference situation, some, let's say, some process description where you will achieve to create good casting. And then if you have this pattern and if you know the technological parameters from the simulation, which can be somehow used on the real machine to make sure that the production will be okay without problems, without defects, you have some reference state. Last but not least is the big data analysis, which can be used later because each of such a machine collects hundreds of data. And if you analyze the data after the process, after the, let's say, 1 month of the production cycle, something like this, you can see the deviation of this reference setup in your production. And if you find some problematic deviation, some deviations which cause the problems, which cause the errors, and the casting which is not able to be used in the following application, then you can analyze what happened that your reference setup is not used. So this is some let's say some idea how we can describe the digital twin of Hypershy die casting process. Of course, it's more than this. It's connected with the visualization of the results. It can be more, but this is something which we can achieve somehow with our tools in the company where I work in ESI. So just to take you a more closer look what Hypershy die casting technology means, you see the machine. Inside the machine, you will put the permanent mold, which is called die because it's permanent. It's a terminology. And you put some hot metal into the chamber, and with the piston, using some pressure, you will transport the metal into the die, and then let it solidify, open the die, put out the casting, and then there are some following operations to be done. But this is a basic, yeah? And this is, of course, there are many variables in the process which can be optimized, which needs to be optimized for each casting produced. I spoke about system modeling. This slide shows the scheme of a very simple Hypershy die casting machine. But this is, when we speak about manufacturing process, the system modeling is more about the producer of the die. Sorry, producer of the casting machine. Have to somehow handle this, not the manufacturer itself. So this part of the process is not really manufacturing question, but of course, to know this and to be to know this and to how this system's working for the machine. This is of course very important also for the plant, for the foundry, where they have to somehow be sure that the machine works properly and without the problems. So this is the first step from my slide, this one, and I will now speak more about the second two. So maybe again, I will give Mr. Kotov the opportunity to translate or summarize.
Спасибо, Vlastimill. Значит, по второй части презентации, здесь мы уже коснулись, собственно, самой концепции двойника для технологического процесса. То есть если чаще всего мы говорим о двойниках, то в основном это говорится о готовом изделии. Это может быть, опять же, какой-то вид механизма, это может быть оборудование, это может быть, собственно, законченный продукт. Но двойник возможно создать также для технологии производства. Что под этим подразумевается? Значит, у нас есть, собственно, технологическое оборудование, на котором мы это изделие будем изготавливать. То есть для него создается классический вариант либо цифрового двойника, либо цифровой модели, ну, или ее называют иногда виртуальной моделью. То есть это расчетная модель, обычно созданная в системе либо конечно-элементного моделирования, либо системного моделирования, для того, чтобы наиболее адекватно описывать, собственно, каким образом эта система работает. Второй большой блок – это, собственно, математическое моделирование самой технологии литья. Значит, здесь мы рассчитываем, как данная деталь будет проливаться, какие возможны дефекты, какие условия ее правильного производства. И один из самых сложных вариантов литья – это, собственно, литье под высоким давлением, который здесь и выбран. Он позволяет производить наиболее высококачественные изделия в достаточно короткое время, но при этом требования к самому процессу, они очень жесткие, поэтому контроль параметров исполнения этого процесса, контроль оборудования становится очень важным. И в этом случае мы уже говорим о так называемой концепции гибридного двойника, который, с одной стороны, использует цифровые данные, поступающие с оборудования, с другой стороны, использует виртуальные данные, которые поступают с математического моделирования. Соединяя их вместе, мы получаем ту самую концепцию гибридного двойника, и вот именно для технологического процесса мы создаем гибридный двойник. Это кратко подводя итоги. Значит, я вижу, что появились вопросы. Значит, по первому вопросу я ответил, значит, по поводу цифровых двойников и, собственно, задачи. Ну, основная задача – это, собственно, возможность данного двойника работать параллельно с реальным объектом, соответственно, контролировать либо его эффективность, либо, если мы меняем какие-то изделия внутри этого двойника, то мы можем посмотреть, насколько поменяется производительность данного двойника, точнее, данного реального изделия. И третье – это, собственно, экономика, это контроль его работы и прогноз жизненного цикла. То есть это вот основные работы, основные задачи для цифрового двойника. И вопрос, который я переадресую Vlastimillу. So, Vlastimill, we have one question is, please explain how digital twins differs from the digital model. So, what is the difference between these two things?
Okay, digital twin versus digital model.
Yes.
the concept of digital twin is really, when we speak about digital model, it's just the digitalization of some application. It's usually some like graphical description of the application or the machine, and it's working with the digital data, virtual data, some simulation, whatever. But the digital twin, what is different is that we are really, as I showed on the first few slides, we are able to let's say feed this digital model with the data from the production. It's the connection between real thing and the digital model, and it somehow speaks from one side to another. So it's a let's say usage of digital model for the optimizing or maintenance prediction for the real application on the real thing.
Окей, thank you. Значит, основное отличие между цифровой моделью и цифровым двойником в том, что цифровая модель – это чаще всего CAD-модель, реже это KE-модель, то есть это модель, которая существует в определенном отрыве от реального изделия. И, по сути, мы создаем копию просто в виде геометрического представления, либо в виде расчетного представления. Что касается цифрового двойника, то данные, которые поступают в дело формирования, идут с реального объекта. То есть получается, что если мы цифровую модель насыщаем реальными данными с объекта, с реального, с датчиков и сенсоров, и она приобретает те же самые характеристики, которые имеет реальный объект, вот в этом случае мы говорим уже о цифровом двойнике. То есть вот это вот отличие. В том, что для существования цифрового двойника нам нужен иметь реальный объект. Thank you. So we can continue.
Okay. So let me skip to the, let's say, another part of the presentation to introduce you the amount of tools which can be right now used by the engineer to, let's say, to switch from the classical trial error approach to somebody much different, which can use the advantage of the digitalization. There are plenty of tools which can be used right now. And the biggest advantage is that the process of this or the, let's say, the usage of the tool starts in the very first moment of the new part design. So yeah, I already speak about the machine, about how the technology of Hypershy die casting works, but let's start from the beginning with the concept of the new part, because you know, when you have a new part, the part itself is usually created based on some you know, function, based on some loads of the operation, which is like it's designed for. But this is the primary restriction of, let's say, the part design. But not usually this part design is also designed with the respect of the manufacturing. So then, if you don't do it like this, if somebody creates a part without taking into account the manufacturing part, it's usually ending up with the very complex communication between engineering and manufacturing department, because it brings so much problems to the manufacturing itself. So the first thing, and this is the first moment when we can really use advantage of the digitalization, is to use something like, for example, in this case, the co-design approach of the simulation software, which can be used with by engineers and also by manufacturers, doesn't matter, but the best way is to be used by both together, designing a new part. So co-design, what it means, it simply means the approach where we spend like most time in the first stage of the process by designing the part and by usage of these tools to do it as effectively as possible, instead of doing it simply without this option and then solve many troubles later during the manufacturing process. You can imagine it on this case, like this is a casting as a part of some chassis. The part is designed somehow, but when the manufacturers tried to prepare the technology to create such a part by casting technology, it was obvious that there are so many problems, so many restrictions which are given by design that from the manufacturing point of view, we are simply not able to produce, or it's too problematic, too expensive, like simply not effective and not optimal. You can see that using another approach, what can be reduced is mainly defect volumes, and it means from the huge percentage volumetric to, let's say, really acceptable values. This is a let's say goal, and I will show you how it works on some very small example. This is the case of Hyperscale casting. This is some kind of cover with so much ribs and different shapes. The casting is quite complex, and of course the parts like this are some, let's say, hotspots from the point of manufacturing of these parts. And if the designer designs the hole in this area, it's not 100% that this hole can be also managed during the manufacturing process. For example, it cannot be casted because it's so problematic. So it will be, the casting will be without the hole, and then the hole will be drilled after. Which brings some more operations, more cost, everything. So the goal is here to really take into account the castability, the manufacturing process, and design the part little bit different if it is possible. Yeah? And how it works in this case, for example, it works on the 5 simple steps. So first, if the designer creates a new model of the part, we only speak about virtual model. So it's a CAD model prepared in different CAD environment. It doesn't matter. This design is somehow used to be analyzed from the geometrical point of view. And based on this first analysis and using some very simple automatic tools to create the simulation of the solidification, it's prepared as thermal analysis of the part. And then the user of this approach has the possibility to review the results for this very small, very short simulation approach. And based on this approach, he will find out what are the critical places of the part, and if possible, and like in communication with the design department, he is able to speak about it and maybe bring some ideas to make the design of the part a little bit different, to simply avoid problems in the manufacturing. And like how easy it is, simply have some CAD model, create the mesh which represents the model in mathematical description for the simulation. And then provide some first look on the geometry, some geometrical design checks, critical section validation, and the problems which are connected with the tool to be used to create such a shape. So of course, it's not only about the casting itself, but it's also about the mold or the tool which will be used to create it. So just to show you how it can work. So we have this very complex casting. And first of all, we can somehow measure the wall thickness of the part. You can see the places where the thickness is the more thick. And of course, this can be a problem. This, let's say, different wall thickness for the part. So if we see something like this, the goal here would be to maybe change the design a little bit to avoid to have such a different wall thickness in the part. Another thing from the castability point of view is the transition between the different thickness. So if we see the case like this, where we have a thin wall and then very sharp transition to the thicker wall, again, it brings much problem. So the goal would be to think about the design and introduce the different thickness transition using some radiuses, using some another geometrical approaches. So yeah, we can see that, of course, even in comparison between two different casting of very similar part, we can have completely different geometry distribution, or let's say the distribution, geometry description of the part, and which makes one part easy to create and the second part very complex and problematic. That's obvious. Then we can, of course, do the also sharp edges analysis. So again, sharp edge is not good from the castability point of view. The goal here would be to create the design as smooth as possible without sharp corners. And from the molding point of view, with this tool, we are able to validate if the casting or the part draft angles are in correlation with how the mold could be prepared, how the mold could be done. Yeah, you can see, of course, if you have such a shape without no angles, you are not able to produce, because you are not able to put it out from the mold. So the goal here would be to do it like this. But last thing here mentioned would be to check also the shape of the mold itself. So if you see the casting shape like this, and this very sharp corner in this area, you can imagine how heated up will be the die in this area, because of the temperature of the metal during the casting is more than in aluminum. For aluminum is about 700 degrees. The die here would have some like about 200, and in a casting moment, when the heat transfer somehow brings the heat from the casting to the die, you will have very, very problematic area here, probably connected with the porosity formation. So the goal here would be to reduce such spots, such areas to minimum, and maybe present a different kind of description of the part design in these areas. And then all this, let's say standard, this geometrical measurement is just a first look on the part design. The second look would be to perform very simple simulation of solidification of the part, because each material has a different density in liquid and the solid state, which brings some problem with the shrinkage of the part. If you perform such a simple simulation of solidification only, one can see quite nicely the problematic area from the solidification point of view. So again, this can somehow means that we have some problems, and to find the solution based on this knowledge, to redo the design based on this knowledge would be the first step to produce the final casting without a problem, and like very nice. So maybe just a very short case or example of this. You can see the part which was previously designed like this. Because of the thickness, the transition of the thickness was quite okay here, but the thickness itself caused the problem. Here, of course, we have some drilling, some machining after the process, and we can see that with the original design, it forms some porosity in the part. Of course, if the part has to withstand some load, it can maybe work as a initiator for the cracks. So after this first picture of the casting, manufacturer or even engineer can bring another idea to make the design a little bit different and reduce this hotspot simply by prolongation of this shape of the casting and reduction of this hotspot like this. Another case would be, maybe let me switch to this interesting article which was done very recently about the virtual prototyping. This is a very nice example of using of this concept co-design in combination with even most advanced approach, which is generic design for the part. You know, it was about such a part. This is an application, and this one is a part itself. And based on some load, based on some description of the assembly, a software automatically creates many variants of this part. This is this generic design, automatic generic design, and it's another level of computer aid for design. Based on this, we choose. This is some outcome of the software. Based on this, we choose some design which was, like, from the castability point of view, most okay, I would say. Then we go through these geometrical checks and the simple solidification simulation. And based on the result of this simulation, the design of the part was changed a little bit. You can see some additional material added here and here, simply to let the solidification goes as expected. We create the original model by additive manufacturing, printing the plastic model, which can be used then for the casting itself, because this case it used technology of investment casting, where you put the model into the ceramic shell. Based on the previous simulation, the second simulation was done, which introduced already some gating system, so the part was very clearly produced without any problem. And at the end, it was really done. The prototype was created and it was without any problem. So this is an approach which really, instead of trial error approach used in the past, is somehow able to bring the healthy casting, healthy part on the first trial, actually. So it's something which should be very appreciated. Okay, Mr. Kotov, please, you can summarize.
Спасибо. Подведу итоги. Значит, большое спасибо еще раз за вопрос по поводу цифровой модели. Собственно, с этой цифровой модели мы и начинаем. Значит, как часть цифрового двойника, цифровая модель должна быть предварительно подготовленная. Но что такое цифровая модель? То есть чаще всего под этим мы подразумеваем все-таки CAD-модель, которая геометрически наиболее точно представляет собой изделие и которая обычно определяется эксплуатационными характеристиками. Если мы хотим создать кронштейн, то он должен выдерживать определенную нагрузку. И, соответственно, исходя из этой нагрузки, мы и проектируем данный кронштейн. Проблема оказывается уже на этапе производства. То есть каким образом данный кронштейн мы можем изготовить. Вариантов много, но не всегда данное изделие, данная модель, она технологически осуществима. И если мы говорим о процессе литья, то здесь как раз очень важными моментами является, собственно, осуществление непосредственно самого процесса заливки и последующего отверждения. И для того, чтобы перейти от конструкторской модели, от идеи, которая сформировалась благодаря, собственно, тем эксплуатационным условиям, к так называемой технологической модели, которая уже будет более полно представлять собой цифровую модель, нужную для двойника, мы должны пройти через этот этап, скажем так, анализа и оптимизации конструкторской модели. Для этого вот как раз один из инструментов, который здесь показан, он называется ко-дизайн, то есть совместная разработка, и она учитывает как конструкторские интересы, так и технологические интересы. То есть идея в том, что вы загружаете в эту модель, в данное ПО, изначальную CAD-модель, которая, собственно, создана конструкторами, а затем мы проверяем, насколько данная CAD-модель может быть изготовлена. То есть осуществляется геометрический анализ, это допуски, припуски, это литейные уклоны. Осуществляется термический анализ, то есть мы смотрим на индикаторы горячих трещин, мы смотрим на зону, где может образоваться пористость, мы смотрим на, опять же, острые углы, которые в итоге приведут к проблемам либо в оснастке, что пойдет перегрев оснастки, либо в самой детали. И, собственно, правим на этом этапе исходное изделие, исходя из требований технологии. Значит, после того, как, собственно, эти правки мы осуществили, мы переходим непосредственно к математическому моделированию самого процесса литья и смотрим, каким образом данное изделие будет произведено. Здесь уже производится полный анализ процесса литья от, соответственно, заливки до кристаллизации. И здесь уже можем изучить не только, собственно, сам процесс заполнения, но и, собственно, какое изделие у нас получится в итоге, какие у нас будут в детали остаточные напряжения, какие будут поводки. И не нужно ли нам сделать, например, компенсацию оснастки для того, чтобы минимизировать эти поводки, либо, например, провести термическую обработку для того, чтобы уйти от внутренних напряжений. После того, как, собственно, мы добились тех результатов, которые нам нужны, мы можем говорить о том, что наша исходная конструкторская модель стала уже технологической моделью, которая не только устраивает конструкторов, но и возможна к изготовлению в литейном цехе. И вот как пример, Vlastimill приводил выдержку из статьи, как раз где полностью весь цикл производства от бионического дизайна, то есть первоначально шла оптимизация самой конструкции, после этого выполнена технологическая оптимизация, изготовлена оснастка и, собственно, осуществлен процесс литья. То есть мы перешли от идеи к реальному изделию. Спасибо. So we can continue.
Okay, thank you, Vyacheslav. Okay, so let's imagine right now we have like the engineer have some part design. The part already take into account the castability of the part, so it's somehow prepared to be produced. In this stage, the engineer have to decide what machine do he use for the production? What kind of setup for the machine itself? What kind of gating design, which means the way how to get the metal into the die cavity. So again, he needs to somehow think about the technological process itself. And based on the cost, based on the production amount, he needs to decide how many pieces he needs to put into die and produce. So again, there are many questions, and even those questions can be somehow answered by using a digital way. Let me take this case of the Hyperscale casting. This is a 4-cavity die, which means that you are producing 4 castings in one shot, in one cycle. This is something like the original design, which the technologist doesn't use this digitalization approach. He simply used some gating concept from the past, from the similar casting anywhere, and it brings some problem. So in this case, what is possible to do is to, let's say, let the program, the software which can be used as an aid for the engineer application, to analyze how the situation looks like with the different gating, with, for example, 5 different versions of the gating system, 5 different ways how to get the metal inside the casting and create inside the die and create the casting. And this tool can be used very simply, with very ease. Doesn't need much but knowledge of the engineer, and it can actually create CAD. It can actually create a CAD model of the gating based on very simple 2D drawing. So in this case, we have the part on the exact position, as it was done for the original concept, but the gating is created with respect of the knowing problem. This is not the approach as it should be, because as it should be, the engineer should can use this approach for the first time to avoid the problematic trial. But simply is not it was not so effective in this case. But this case shows the effectivity after we implement this tool. So the way how to get the metal inside is simply created based on the 2D sketch of the gating and the knowledge which is somehow implemented into the software. The knowledge which knows exactly how to create the shape of the gate, how to create each gate channel, gating channel. So this is used. By this method, one can analyze very fast in virtual space many different variants how to get metal into die, how to create the casting from so many variants which are created very fast just using a 2D sketch done by CAD environment. And if the engineer will do that like this, the software will give him many important information which is necessary to know before the production of the casting can start. The second aspect of this computer-aided approach is to be also able to choose the right machine to create such a part, because of course if you are casting only one part in one die, you need completely different setup than if the die is for example 4-cavity die, as it is right now in our case, because the amount of metal is much bigger. You need the machine with the much bigger force to be able to close the die and hold the die in the process of filling. So what machine you die, and do you have this machine in your factory? This is again something which can be answered by the program, where you can see the model is already completed with some description of the chamber here. So we have a whole assembly for the casting, and we can decide which material will be used and which machine which will be used for the production from our selection. Of course, the machine itself can be a part of some database in the software with a description of some basic description of the machine. And after analysis, in case we choose the right machine for the casting, we can see our setup lying in the operating window of the machine, so we are able to produce it without the problem. This is again the approach introduced in the software. And if you see the result of this after introduction of this gating and creating a simulation of the filling and solidification process, we can see that from the original design, where not all the casting was filled, there was a problem with filling, and each casting was filled in a different time, which is problematic from this technology because you need to know exactly the right time to start the higher velocity of the plunger here. So in compare with the original design, this new one introduced much bigger casting pattern, the filling pattern, and reduction of the problematic of the errors, which was created here by the basic design. It is also quite visible that let's say the comparison between the simulation result and what happened in reality is very close to each other. You can see when the machine was stopped in some time, the metal is in the exact position as it was in the simulation. So it was just the confirmation that the design produced with this approach is really useful. The last thing of this block would be to know that in these days, what was prepared in a virtual space can be very fast transport to the real machine. In this case, you have some description of the piston movement during the filling stage, and the exact curve was simply exported into the software of the machine, which in reality creates the casting or replicates the process from the virtual to the real production. And of course, it can also work vice versa in case you have some problems with the filling. The user or the engineer is again able to get the curve, use it in the virtual space, and analyze what can be the problem from the filling point of view, because of course in the reality you don't see what happened inside the die. You can see it only in the virtual space, and you can then decide based on the visualized filling pattern what to do differently, and maybe also even let the software, let the virtual space optimize the process based on some criteria. Okay, Mr. Kotov, please summarize again.
Да, спасибо, Vlastimill. Значит, теперь двигаемся дальше. То есть на этапе проектирования мы, собственно, создали отливку, которую можно произвести. Теперь, собственно, каким образом мы ее будем производить. Первый этап виртуального производства – это выбор, собственно, системы питателей. То есть каким образом будет подаваться металл на данную отливку, сколько отливок можно изготовить одновременно, если мы используем дерево отливок, при использовании, опять же, той же самой технологии литья под высоким давлением. Значит, здесь есть специальные инструменты, которые позволяют на основании наших идей, на основании, собственно, набросков, чертежей создать систему питателей, то есть подобрать диаметр, подобрать расположение и, собственно, оптимизировать ее по времени заливки. Это первый этап. Второй этап, собственно, необходимо понять, на какой установке данная деталь будет пропитываться, то есть какая из машин подходит под данную технологию, какая нет. То есть исходя из давления, исходя из скорости подачи металла, исходя из размеров рабочей зоны машины, мы можем выбрать, введя данные параметры в ПО, мы можем выбрать ту или иную машину в окне оптимальных параметров. Соответственно, мы выбираем скорость заливки, выбираем давление и выбираем то самое окно, в котором эта деталь будет произведена максимально быстро, но опять же с минимальными дефектами. Соответственно, этот этап уже идет на выбор машины. И последний этап – это, собственно, каким образом нам соединить наш расчет, наше математическое моделирование непосредственно с оборудованием, которое будет использоваться для процесса заливки. Здесь есть возможность передачи различных данных на машину. Ну, чаще всего для литья под высоким давлением наиболее важная часть – это, собственно, график давления, ну или график скорости движения плансона. То есть в каком этапе у нас идет низкая скорость для первоначальной заливки, и, наоборот, более высокая скорость, когда металл уже, ну, скажем так, заполняет самые дальние зоны отливки. То есть вот этот вот график, который мы определили на математическом моделировании, мы затем уже передаем на установку для того, чтобы на установке его с точностью воспроизвели. Vlastimill.
Thank you. Okay. So this was the second step, let's say. In the first step, we defined how the design should be made to respect some some manufacturing point of view. The second step is just a tool for the manufacturer to be able to, let's say, design the technological process itself with the help of computer aid. The third block would be about description of the whole process, because I mentioned it during my, let's say, introduction of the design of the digital twin of casting process. I spoke about simulation to be used as a reference for some optimal settings for the machine. But of course, if we want to have a reference setup, we need to take into account as much as possible. We need to describe the process of production of casting very well with the accuracy as possible. So for this, the slides which I previously shown wasn't enough, because we really need to know the thermal distribution of the die, what happened with the casting during the filling and solidification, but again, what happened with the die also, because it's thermally, it's heated up and then cooled, and so there is some kind of thermal cycle, which it's a problematic for the die. And we can also we need to analyze what happened with the casting after the ejection from the die. So what happened when the die is open and the casting goes out, and then some following operation. So we need to be able to describe it whole. And again, this slide shows that we actually are able to do it so we can introduce the cycling phase, filling, solidification, then par, ejection, and cool down. And even the influence of what happened with the residual stresses and how the casting will deform after the cutting of the gating system and heat treatment, for example. This is just an example which really takes into account all the case. But let me use another case to show the most advanced approach for the simulation of Hyperscale die casting technology. It's about battery cover for electric vehicle. So it's kind of modern part, as you can say. The blue part, not exactly the one, but the very similar. It's shown here on this graph, where we started from the CAD, performing many simulations of, for example, cycling with stress, then getting a new kind of shape of casting after the thermal expansion of the die, and then standard filling, solidification, calculation of deformation and stresses inside the die, and then what happened after the casting is ejected from the die. This is the whole process, and only this can be somehow considered as a reference for the process setup. And in this case, just to be like more clear how why the simulation can be a reference, we are comparing two variants of the casting, which will be seen here. We have the variant. This is not like original and or like optimized variant. It's just for few, like the second or the two different variants of the same casting, but with some expected behavior, which can be known by the engineer from the previous experience. So the first is the design from the designer, and the second is the design which already applies some manufacturer view. So in this flat area of the casting, some ribs are added to hold the casting to, let's say, avoid the deformation. This was a like pre-thinking about before the casting was created. But of course, we can simply arrange these variants because we are speaking only about digital or virtual approach. So then it was not about filling only, but the whole die was introduced with the cores, like all the assembly which is used on the machine to produce the casting, and also all the cooling channels, because the die is completely drilled, because we need to somehow be sure that the casting is having some pre-described temperature, because we need to have this die. This die is permanent, but it doesn't necessarily mean that this can be used forever. Of course, with the temperature, with the influence thanks to the temperature from the casting and from the process itself, it's degraded, and then it can be also then it can crack or can be destroyed. So these channels are the way how you put the material in the temperature which are somehow okay. And this is also introduced for in the simulation. So the simulation really described the real setup. Yeah, so we can see the final state of the die after some number of cycles. Each cycle brings some heat up of the die. Each cycle brings some cool down using the cooling channels, using the treatment of the surface of the die. So in the first stage of the simulation, we are looking for the steady state. If we have this steady state, we can say that we know the temperature distribution of the die, and we can continue with the another simulation. And this cycling is presented here. You can see we are in the 5th cycle now, so you can see how many cycles is calculated. It's probably 10, and by 10 times magnified, you can see the thermal expansion of the die. So the die is really heated up, and it goes bigger because of the thermal expansion. After this calculation, from the 0 model of the casting, the new model was closed, which also taking into account thermal expansion of the die. And this new model was used for the calculation of filling and solidification, like it is visible on the video. So we can see both variants, very similar from the filling point of view, very similar, but we can see how different will be from the stress and deformation point of view. So before the casting is ejected from the die, we have some distribution of the stress, and then the casting is removed from the die, which brings some spring back effect, which means that the stress which is generated in the die relaxed and became deformation. And we can see the deformation on the slides. And it's so visible how the first variant without the technological ribs is bending a lot in compare with the second one, which is bending also, but with a very big difference here. If we check the situation from another view, you can see the bending effect, which is enormous here. Of course, this is not the bending of the real casting, it's 25 magnified, but because it's not so visible just by the eye, but it's visible here. And of course, with the bending like this, there is no way how to assemble this part of the battery with the second part of the cover. Yeah, so the problem was like to have this bending. It was really not acceptable. And you can see during the virtual phase, without preparing any real casting, that simply you cannot achieve the goal without this supported technological rib. And again, you can even play with the system itself. You can play with the cooling intensity for the die. You can play with many different things to prevent this bending effect. Even if you have this rib, you could see that there is some bending of the parts. This can be simply solved, or not simply, but it can be somehow solved playing with the setup. Okay.
Okay, so I will sum up. Значит, собственно, если мы говорим о двойнике технологического процесса, то, естественно, основная цель – это правильное осуществление самой технологии и оптимизация данной технологии с точки зрения либо снижения брака, повышения качества материала или определенных эксплуатационных свойств. Значит, чего мы можем добиться, применив математическое моделирование на данном этапе? Значит, первый блок, собственно, это оптимизация оснастки. То есть, если мы говорим о литье под высоким давлением, то наибольшее напряжение, естественно, на себя принимает оснастка, а оснастка используется в данном процессе не один раз. Соответственно, мы должны учитывать эффекты, которые возникают в оснастке при ее нагреве и охлаждении. Вот эти термоциклирования, они, естественно, вызывают постепенный износ оснастки и выход ее из строя. Соответственно, первый этап оптимизации, который может быть, это, собственно, оптимизация по каналам охлаждения, которые применяются для компенсации высокой температуры в оснастке. И второй блок – это, собственно, сами термоциклы. То есть мы можем посмотреть влияние термоциклов на стойкость данной оснастки. Это первый блок. Второй блок – это, собственно, оптимизация самого технологического процесса. Здесь мы можем говорить как оптимизация геометрии, так и оптимизация самой технологии. В том примере, который показал Vlastimill, используется деталь – это часть аккумуляторной батареи, то есть это крышка аккумуляторной батареи, которая применяется в настоящее время в электромобилях особенно активно. И данная деталь, она очень тонкостенная, поэтому для ее производства как раз применяется именно литье под высоким давлением. Но первоначальный вариант, который был вынесен на суд, он имел ребра жесткости в одном направлении. И, естественно, когда этот вариант просчитали, данную деталь очень сильно увело. То есть получилось, что очень большие корабления, и ее просто установить в сборку невозможно. Вторым вариантом, который был предложен, является использование ребер жесткости в двух направлениях. Также этот вариант был просчитан с точки зрения изготовления. По самой технологии изготовления проблем не было, и остаточные корабления, которые возникли после того, как деталь, собственно, остудили, достали из оснастки, остудили, они были в разы меньше по сравнению с первым вариантом. В итоге эту деталь удалось произвести и, собственно, установить уже в сборочную единицу. Соответственно, цель, как я сказал, цель двойников технологических процессов – это, собственно, качество изделия и желательно, естественно, и стойкость оборудования, стойкость той оснастки, которая используется для производства. Окей, Vlastimill, you can continue.
Okay, so you know, you would say maybe the whole time I spoke only about the simulation and like this part when I introduced the digital twin of casting machine. I just spoke about this, but this is something, you know, just to understand that the simulation is used here as a something like a description of the reference setup of the machine. Right now, we will also introduce the way how to collect the data from the machine and then analyze it and then see the differences or deviations in compare with this reference system, because of course it's not so easy to simply use the data coming from the simulation, use it for the setup of the machine, and then produce healthy casting. Is not the case. In the real, there is an operator of the machine. There is many different conditions of temperature, of the production values of the system of the machine. So some like in a so much cases the situation simply have to somehow be improvised, but we need to learn from this, and collecting the data from the machine, we are able to, and analyzing it, we are able to learn, to find some connection between the production data and the defects of the casting, and then this is about the last block will be about this analysis. So again, to use the production data to go through some big data analysis tool, and then increase the efficiency, quality of the casting, and decrease the scrap rate. So this approach, which will be presented here, is the mindset approach. This is a software which using the machine learning, data analytics, and data visualization. The visualization is the big part of the casting of the process here, because of course, if you have a data and you are not able to visualize them, you know, you don't need to have a data. So this is a big goal to achieve here, to let's say have an environment which really gives the user or engineer the tools to visualize the data as nice as possible. And of course, to visualize the data, one can use many different kind of approaches, graphs, different kind of visualization here. I will go through it. But the first and most important things before we can speak about big data is to be able to connect data. Of course, the machine, Hyperscale casting machine, is producing, for example, I don't know, hundreds of casting per day, maybe thousands. It's really the shot it's taken, like it's the shot. One shot, one casting is performed in below 1 minute. It can be so. You have really a huge amount of data if you want to trace each casting. If you want to trace it, you need to somehow mark it, and there are plenty ways how to mark the casting. But in this case, it's one example, and in this case, really, each casting which is produced have this mark, and the mark contains full description of the setup of the machine. So within this mark, you can find out the temperature of the metal, you can find out the temperature of the cooling media and the amount of cooling media going through the channel. You can simply find out everything. You can see the velocity, you can see the pressures, everything. And then, of course, you can connect this data from the machine, from the production, with the quality data which you get after you produce the part and validate the part, make some tests, and validate the quality. Let me show you this on one example of two parts, two castings. one is called 855, second is Untitled 56. These are two castings, but it creates one assembly. The casting is separate. Of course, you first produce one part and second part. Then both parts are marked. They are trimmed, which means that the gating system is cut it off from the part. And after machining, those parts are joined by electron beam welding technology. Together, final assembly of these two castings goes to the machining again, and then because it's a part of the heating in the car, and there is a medium goes through it, it has to be it has to prove in the leaking. So the helium leak test is used to assess the assembly. And you can see that there are surfaces on the casting which are somehow named by the defect code. Then you can see the amount of parameters which are going through from the machine. We simply need to handle all this data somehow, and here this slide shows some mathematical logic which is behind the preparation of the data for the tool, because of course you have some production data, but then you have the quality data from the machining, you have quality data from the welding, then quality data from the leak test, and all this data have to be somehow connected based on some value, based on some common thing, which is here the number of the mark from one and another casting. And then you can analyze. So this is how the environment looks. It creates some basic analysis using a standard Gauss approach. Like you can see the average values of each of the parameter. And for example, here we can already see some interesting thing, which is high velocity of the plunder, high speed. Yeah, we can see that we have two maximum here. Knowing that the part was produced on two different machines, it's a T65C1, T6050C3. So we can see that there is two different kind of setup for the machine which can produce the part. Knowing that, of course, it was only one prescription for the process. It's not two. So from some reason, the approach was changed, and one machine uses different speed of the plunder. From 3.5, it goes to 3.2 or 1 in the second machine. Of course, we can have some. We can have also healthy casting here, but does it cause some problems? Does it create maybe some defect which this machine cannot? Maybe we can analyze, and yeah, that's it actually. This is the analysis. We can see the defect code here, and if I run the simulation, I can, for example, choose some defect and see what combination of the parameters of the machine leads to this defect. And if I see that the one defect is caused only by high speed, I can say, okay, this setup of the machine is wrong, needs to be changed, and it doesn't correspond with the reference setup, which was somehow validated and find out thanks to the simulation approach. So this is simply, for me, this is a connection of the real data and the simulation or the virtual data here in this case for Hypershy die casting machine. It's not maybe so clear as it was in the example of this steam turbine, but this is simply the approach which can be somehow and which is somehow called digital twin for manufacturing process, connecting with the casting. Just to mention, we are right now part of the government project in Czech Republic, where we are really trying to connect all this together to have, let's say, smart die. This is the name of the project. And the ultimate goal here of the project is to be able to predict, measure the data of the real production and predict based on the measurement of the data, die life cycle, the fatigue of the die, because of course, this is the main goal of the production, to be able to use the same die for as much as possible casting, because of course what is the most expensive here is the die itself, because it's like from the special materials and quite expensive. So this is all from my side. I believe it was somehow interesting for you. I will just let Mr. Kotov summarize also the last part, and then of course if you have some questions we can go through it.
Thank you, Vlastimill. Значит, и в завершении презентации мы бы хотели вернуться, собственно, к начальной концепции цифрового двойника. То есть мы рассмотрели с вами математическое моделирование и каким образом его можно использовать для оптимизации технологий, для повышения стойкости оснастки и для, собственно, повышения выхода годного. Но каким образом эти данные можно связать непосредственно с реальным производством, с реальным изготовлением деталей. И здесь на помощь приходит система анализа больших данных. То есть в современном оборудовании есть большое количество датчиков, которые могут быть использованы как элемент сбора информации о технологическом процессе. И как раз вот этот анализ, он позволяет нам связать мат-моделирование и реальные данные. Вот тот пример, который Vlastimill здесь привел, это данные с реального производства под литья под высоким давлением. И на производство собирается большое количество технологических параметров. Это и скорость, например, движения Пуансона, это скорость заполнения металлом, температура, влажность, то есть большое количество параметров, которые собираются непосредственно на оборудовании, либо на территории самого цеха. И идея анализа больших данных в том, чтобы установить связь между дефектами, которые возникают на изделии, и, собственно, теми производственными параметрами, которые мы собираем в качестве данных. И вот как раз анализ больших данных, он позволяет установить взаимосвязи, установить причинно-следственные связи и определить, какие настройки оборудования привели к образованию дефектных изделий. Но это так называемый первый блок, когда мы работаем только с оборудованием, только с данными, не переходя на математическое моделирование. Но нам надо соединить эти две вещи, и вот тот проект, который вот сейчас на слайде у вас показан, это как раз проект «Объединяющие данные». Значит, примером такого объединения может быть, скажем так, уточнение математического моделирования благодаря данным, поступающим с оборудования. К примеру, у нас в какой-то зоне на термопаре температура выше, чем на мат-моделировании. Соответственно, у нас в мат-модели деталь будет охлаждаться быстрее за счет того, что температура в этой зоне ниже. И вот как раз те данные, которые поступают с оборудования, они будут, скажем так, отправлены на мат-моделирование, на уточнение, например, данных по температуре в этой зоне. Соответственно, модель обновится, и она уже будет рассчитана с новым распределением температур по поверхности. Вот это как раз пример взаимосвязи между реальным оборудованием и, собственно, математическим моделированием. И тот проект, который здесь сейчас представлен, это проект, который, собственно, происходит в Чешской Республике. Партнерами являются университет с компанией Mecas ESI и, собственно, изготовитель данных изделий такого лис. И цель данного проекта, который называется цифровая оснастка, это, собственно, создать полный двойник для данного процесса и оптимизировать жизненный цикл оснастки. То есть нам нужно будет не просто просчитать этот жизненный цикл условно говоря, в циклах, сколько циклов выдержит эта оснастка, но и найти оптимальные значения технологических параметров, при котором деталь будет по-прежнему качественной, но оснастка будет как можно дольше стоять на данном оборудовании. Потому что основная цель, основная цена и основная стоимость для литейных процессов, ну, в частности, для литья под высоким давлением, это, собственно, стоимость оснастки. И вот этот проект запланирован на ближайшие 3 года, собственно, как раз представляет собой то, о чем мы начинали с вами говорить. Это пример гибридного двойника, объединение реальных данных цифрового двойника и объединение математического моделирования, так называемого виртуального двойника. Вместе мы получаем гибридный двойник для технологического процесса. Yes, Vlastimill. So I finished for the moment. I see several comments that people thank you for the very interesting lecture. So if there are no questions for the moment, so I think I will have a couple of them just to, let's say, to make some notes on what we discussed. So you're ready, yes? So the first question is regarding the optimization which you showed. So you showed really the optimization based on the design of the casting, so which you can do on really early design stage. But what other kind of optimization can be done in simulation? What you can optimize?
Of course, yeah, you can optimize more things than I described in the presentation. In these days, like what is quite familiar for the users of such a simulation, actually all the project variables can be somehow optimized. So if you, for example, imagine the most clear things of the let's say the thing which is problem of each casting, which is shrinkage defect in some hotspot, one can use this defect as a criterion for the optimization, and many variables of the process as a variable of the optimization, which means the temperature, cooling, pressure, whatever, or even combination of those. And then system or automatic optimization system can run various number of simulations, which can then lead to find the optimal combination of the variable to have, let's say, the less possible porosity in some area of the casting. This is one of the, let's say, common example of the optimization, but of course, you can also optimize the pressure curve. You can optimize, for example, the amount of air which is entrapped in the casting because of some wrong velocity pattern or wrong filling. Simply, there are many things to optimize, to be optimized. Not only design, but also technological parameters.
Thank you, Vlastimill. То есть мы обсудили возможности оптимизации, используя математическое моделирование для нахождения оптимальных параметров. И помимо той информации, которая была показана в лекции, что касалось именно оптимизации на раннем этапе конструкторской детали, оптимизировать можно большое количество технологических параметров, температуру заливки, давление, скорость. И, собственно, критерием для оптимизации будет, естественно, получение качественной отливки с нужными свойствами. То есть вы можете задать уровень пористости, можно задать механические свойства, которые нужно получить, и за счет циклов оптимизации, собственно, можно добиться улучшения данных свойств. And the second question is, let's say, it's more regarding twin and hybrid and digital twin. So when we receive the information from the equipment, we have the data in real time. So if we really want to create some kind of hybrid twin, the system model, okay, it can work in real time, but regarding CAE simulation, finite element method, usually any calculation takes hours, sometimes even days. So how we can handle this problem and how we can make hybrid twin operate also in real time, that's like a real process or real device?
Yeah, that's a very interesting question. Of course, it's the situation as I described it is showing some, let's say, to find out some reference description of the process like offline, and then use it in the reality, in the real process, and then let's say maybe check some deviations of this process. But the ideal state would be to introduce also a real measurement and the way how to really fast react on the changes which will occur during the production process by this measurement. So, for example, during this project, the Smart Die project, we will also introduce the measurement capability for the die to measure temperatures, pressure, and even maybe tension, some stresses, and to be used as a real-time validation of what happened with the die. And maybe one of the way, which I'm not really expert on, but it's a PGD approach, which combines many of simulations, which together to let's say to have some knowledge about what happened, what can possibly happen in the process using this very big amount of simulation of each state. And then using this knowledge, it can provide the simulation even in the real time. But it's maybe for the separate lecture, and I'm not really expert of this topic. But I know there are already some approaches.
Thanks a lot, Vlastimill. Значит, второй вопрос, который я задал, касается возможности расчета методом конечных элементов в реальном времени. Так как реальный объект действует у нас, естественно, в реальном времени, то необходимо, чтобы двойник мог работать в реальном времени, иногда даже быстрее, чем реальное время, и мы могли видеть на двойнике проблемы, которые возникнут в реальном объекте, через какое-то время. То есть он должен в реальном времени отрабатывать ситуацию и делать какой-то прогноз на будущее. Любой конечноэлементный анализ, он требует определенное количество времени на расчет. То есть если мы говорим о расчете литья, то это могут быть часы. В очень сложных случаях это могут быть десятки часов. И, соответственно, ни о каком возможности расчета в реальном времени мы не ведем, если мы используем классические методы. Значит, что нам позволит рассчитать систему в реальном времени? Первый блок – это, собственно, системное моделирование, то есть моделирование на базе простой математики и 1D-систем. Что касается конечноэлементного анализа, то есть специальный механизм, например, то, что Vlastimill сказал, это PGD. Это механизм, который позволяет, имея определенное количество предварительных расчетов, то есть мы сделали расчеты с различными технологическими параметрами и накопили определенную статистику, то есть определенные сочетания технологических параметров, которые в дальнейшем уже будут использоваться для создания модели, так называемой модели пониженного порядка, которая позволяет изменять данные параметры в реальном времени. И вот в этом случае как раз вы можете вот эту модель пониженного порядка, модель реального времени встроить собственно, в концепцию гибридного двойника. И такая модель, в частности, будет использоваться для данной системы, для гибридного двойника оснастки в проекте с Ковалисом. То есть здесь будет собираться информация по оснастке, по температуре, по давлению, по напряженному состоянию. И эта информация будет сравниваться с математическим моделированием и, соответственно, вводиться будут какие-то корректировки. Данная тематика по расчетам в реальном времени – это, собственно, тематика отдельной лекции. И если это будет интересно, то мы можем отдельно организовать, собственно, мероприятие по тематике расчетов КЕ в реальном времени. Thanks a lot, Vlastimill. So I think that's all from my side. I see again some comments that you big thanks for the lecture. And so maybe Valentina or Vasily, so you can say some words just to finish. Валентина, Василий, мы закончили. Может быть, у вас какие-то вопросы или комментарии? Так, есть небольшая задержка на YouTube, поэтому, возможно, еще Валентина пока не получила вопрос. Валентина? Так, ну, если вопросов нет, комментариев нет, что я скажу еще важно для тех, кто будет смотреть данное мероприятие в записи, чат будет работать, поэтому если у вас будут дополнительные вопросы по данной тематике, то, пожалуйста, задавайте на русском, на английском языке, мы постараемся оперативно отвечать на данную тематику. И если есть вопросы непосредственно к Vlastimillу, то также задавайте в чате, я, естественно, ему передам. Все, тогда спасибо большое за внимание. Тогда мы отпускаем Vlastimilla. И еще раз спасибо за время. Мы несколько превысили лимит, который нам предполагался, но думаю, что тематика была интересна, и в дальнейшем мы будем ее развивать. So, thanks a lot, Vlastimill. And,
Thank you, Vratislav.
And bye-bye.
Thank you, bye. Wish you Merry Christmas, actually.